start record. So already, so we are still in chapter 7. So I start slide number 8. Slide number 8, chapter 7. So chapter 7, we are still in chapter 7, and slide number, I start today with slide number 8. So talks about the ionization energy. Ionization energy or ionization potential is the same thing. So this is ionization energy. What's the spelling? Ionization energy. So or ionization potential, same. Either IE or IP. Sometimes we call ionization potential, or sometimes we call the ionization energy, is the same thing, yeah? So what is ionization energy? You have an atom here, let's say, you have an atom here, let's say this is a neutron proton here, a neutron proton in the nucleus here, here is the electron. So this is in the ground state and is the gaseous atom. So this is in ground state, meaning that it has not absorbed any energy previously, right? It's in the very natural state. It's a ground state, and it is in the ground state and is a gaseous atom. Gas. This is a gas atom. It's not a solid atom. It's not in solid. It's in the gaseous form. Yeah. Now, how much energy you need to give this one? Let's say it's called I1. This is the amount of energy. Yeah. So we need to give some amount of energy to this one so that this electron completely goes out from the atom. Yeah. So that's called the ionization energy. So this becomes like this. So this is a neutron proton here, and the electron is gone. So this electron is completely gone. So I might write this one like this. This is the electron. Yeah. Make sense? So when the atom is in the ground state and is in the gaseous state, we give some energy to this atom, and the minimum amount of energy that we give that atom so that the electron is completely detached from the atom is called the ionization energy. Make sense? Or ionization potential. So, so this is the ionization energy. Now let's talk about one example I give here for the potassium. So this I talk about the hydrogen. Now let's talk about the potassium. So here is an example, potassium. So this is a K is a potassium atom. So this atom is in the gaseous state. G means gaseous state and is in the ground state. It has not absorbed any energy previously. Yeah, ground state means it has not absorbed any energy previously. So it has how many electrons in the outermost orbit of potassium? There is one, right? Potassium is in the group 1 element, right? So potassium is in the number 11 box. So if you look the electronic configuration, inside is potassium is 11? I don't know, whatever is in the group 1. So outermost outermost electron, there is only one electron in the outermost orbit of the potassium. Yeah. So because it's the group 1 element. Now I want to give some energy to this potassium atom. So let's say this is ion. So I give some amount of energy. This ion means not iodine. It's an amount of energy. Yeah. So I give some amount of energy, and it knock out that one electron from the outermost orbit to give K plus, and the electron is completely gone from the atom. Make sense? So this is called the ionization potential. So what is the requirement for ionization potential? The atom should be in gaseous state and the atom should be in the ground state. And we want to take all the outermost electrons from it by giving some energy. And that is called ionization energy. So how much energy we should give to this potassium so that this electron completely goes out? So that amount of energy is 419 kilojoule per mole. So meaning that if you have 6.023 10 to the power 23 atoms of potassium gaseous atom, you need to give 419 kilojoule energy so that all those 6.023 10 to the power 23 potassium atom becomes the potassium ions. Listen? So like that. So why is the plus here? Because here is a vessel. Maybe here is a vessel. Here is a vessel. So we have a 1 mole of potassium ion, meaning that 6.023 10 to the power 23 potassium atom in gaseous phase. So if I give 419 kilojoule energy here, all these electrons are just detached and gone. Make sense? So that's what we are saying. So if you give here 419 kilojoule heat energy or something, this reaction happens. Good? So good. Now this is called first ionization energy because I just removed the first electron. Yeah. If you remove the first electron, that is called first ionization energy. And then if you remove another electron again, that is called second ionization energy. If you remove another electron by giving energy, that is called third ionization energy. Yeah. So this is first ionization energy. They call right the I1, meaning that this is the amount of energy to remove the first electron from the potassium ion. Now let's talk about the second ionization energy. We are already done with the first ionization energy. It's already in the K plus form, right? K plus. Now we have K plus here. There is no electron in outermost orbit. There is only electron in the inner orbit. Yeah, there are 8 electrons in the inner orbit. Now I want to remove the another electron from the inner orbit, and then that becomes K 2 plus. 2 plus. So this is also gas. This is also this is the energy, and this is the gaseous form. And then what I have is I remove another electron from the potassium ion here. Make sense? So this one is 3000. How much energy I need to give here? That is 3051 kilojoule per mole. Too much energy. To remove the first electron, you are just giving 489 kilojoule. To remove the second electron, you have to give a lot of energy, 3051 kilojoule of energy. Why we do like that? Why the energy, second ionization energy is so big? Because it's like this. So let's say this is a potassium atom. So this is a, I think it's a 19. So potassium. Do I have a periodic table here? So what is the potassium? That's 11, 12, 13, 14, 16, 17, 18, 19, 20. So the potassium is a 20, number 20th box, right? So this is the potassium. So in the first, so we have a proton and neutron here. So in the first orbit, there are 2 electrons. In the second, 1, 2, 3, 4, 5, 6, 7, 8 electrons. And then we have 1, 2, 3, 4, 5, 6, 7, 8 electrons. And then we have 1 electron in our outermost orbit, like that. So if 2, 18, 10, 18, 19, whatever. It's I'm talking about outermost electron first, right? So to remove this electron, I just need 419. When I remove this one, where should I remove the electron? Another electron. I need to remove electron from inner orbit, right? So inner orbit is already full. 1, 2, 3, 4, 5, 6, 7, 8. It takes too much energy to break the full cell. If the cell is very full, it has 8 electrons in its orbit, so it takes too much energy to take the electron out from the full cell or half cell. Yeah. So to remove this electron, it takes very high amount of energy, almost 7 times higher. So first ionization energy is to remove the electron from the first orbit. Second ionization energy is to remove the electron from the second electron from the, could be from the first orbit or could be from the second orbit. Yeah. Make sense? Good. Now, like that. Now, so periodic trend of ionization energy. Let's talk about the periodic trend. So this is from the last class. So if you see here, lithium is here, and beryllium is here, boron is here, carbon is here. So to remove the first electron from the lithium, it takes 513 kilojoule of energy. To remove the electron from beryllium, it takes 899 kilojoule of energy. To remove the electron from boron, 801. To remove from carbon, 1086. To remove the electron from nitrogen, it takes 1402. And to remove the electron from oxygen, 1314. And from fluorine, it takes 1681. And from neon, if you want to remove the electron from the outermost orbit of neon, it takes 2081, like this. If you see here, the trend is, this is a small number, it's a bigger number. Forget this number for a while, this is even bigger number, this is bigger number. Forget this number for a while, this is bigger number, and this is even bigger number. As we go from the left to right in a group, the ionization energy increases, right? There are some anomalies, I will talk a little bit later. So this, don't look this number there. And don't look this number here. And 13, 14, 16, 18. Yeah, look here. So it's a, if you see the general trend, if you move from left to right in a period, the ionization energy is increasing, right? So we need to give more energy to remove the first electron of neon. A lot of energy here. To remove the electron of the fluorine, we just need 1681. For oxygen, we just need 1314. But for lithium, we just give 513 and electron is gone. So why is that? The reason is, we already talked in the previous class, as we go from left to right, the effective nuclear charge increases, right? So when the effective nuclear charge increases, the electrons are pulled very strongly toward the nucleus, and it is hard to remove the electron. Make sense? So basically, as you go from here to this way, the effective nuclear charge increases, the size decreases, right? And then it is very hard to remove the electron from the smaller, highly attracted electron toward the nucleus. Make sense? Good. So like that. So because why this happens? Because effective nuclear charge increase going from left to right. And when the effective nuclear charge increase, the proton of the nucleus attract the electron with very strong force toward nucleus, and it's very hard to remove the outermost electron. Make sense? Good. So effective nuclear charge increase on going from left to right. Now let's talk here. So that's lithium. Here is a sodium. Here is a sodium. Sodium has 496. And here is a potassium, which is a 419. 419. So if you look here in the group, when I go from top to bottom in the group, if you see here, this is 513, very large number. Sodium, smaller number here, and potassium, even smaller number. Why it happens? Because as we go down from the from top to bottom in a group, as you go from top to bottom, what happens is lithium is like this: hydrogen, helium, lithium. So it's a number 3, right? So lithium is like this. So two electrons, there are protons, and lithium is like this, right? It's too big. Make sense? So we are removing, too small. So we are removing this electron from here. So we need to give 513 kilojoule of energy to remove that electron. How about the sodium? Sodium is number 11. So let's write that one. So that's a proton neutron. So 2 electrons here. Then we have 8, 4, 3, 4, 5, 6, 7, 1, 2, 3, 4, 5, 6, 7, 8 electron here. And then we have another electron here, like this. It's too big, right? This atom is too big, right? So it is easy to remove this electron than this electron. Yeah. So if one is very far from the nucleus, it is easy to remove that one. So it has smaller. It needs smaller amount of energy to remove this electron, but it needs large amount of energy to remove this electron. Why? Because the size of this is small, size of this is very big. Yeah. So it is easy to remove the electron from the big size atom. So why? So as we move from top to bottom in a group, size of the atom increases, and when the size becomes bigger, the outermost electron can be removed very easily. Make sense? Good. So how about here? If I put the potassium, so I would feel like this. Potassium would be like this. So potassium would be like this. So this is a proton neutron here. In the first, I have 2. In the second, I have 8. 1, 2, 3, 4, 5, 6, 7, 8. And then another I have. This is first, second. Another I have 1, 2, 3, 4, 5, 6, 7, 8. And then another electron is outermost here. So this is potassium is even too big, right? So it is much easier to remove that electron from that large atom because it is not being attracted that much with the nucleus. Make sense? Good. So as you go from top to bottom in a group, ionization energy decreases because the size of the atom becomes larger. This is smaller, this is larger, another one is even larger, another one is even larger. So when the atom becomes larger, it is easy to remove the electron from the outermost atom. Yeah? So the ionization energy decreases on going from top to bottom in a group. Now, let's go to slide number 10. the number that I crossed here, I will talk later about in the anomalies of the ionization energy. Yeah. So how about this one? Removing more than one electron. So I'm in the slide number 10. So let's say lithium. So lithium. So first ionization energy. So let's draw the electronic configuration of lithium. So lithium is number 3. So neutron proton here, 2 electron in the first orbit, and one outside here. So to remove the first electron from the outermost orbit, it is called the first ionization energy, right? So if you want to remove this electron, how much energy you should give? You should give 513 kilojoule per mole energy just to remove this one. Now, if you want to, so this is first ionization energy. First ionization energy. So you already removed this one by doing this one. Now, another electron you should remove from here in the second orbit, right? So second ionization energy, you need to remove the electron from the inner orbit. So second ionization energy is 7,298 kilojoule per mole. And why first ionization is very small? Why? Because we are removing the electron from the outermost orbit, which is very far from the nucleus, right? It is easy to remove that one. So why it is harder to remove this electron by giving large amount of energy, like about 6 or 7 times, right, of the energy. So because we need to remove this electron from the inner orbit, which are being pulled more strongly by the nucleus, right? So it's very hard to remove this electron. Now let's remove the third electron, third ionization energy. So if you want to remove this electron, it experiences even more force from the this proton here. So proton were 3 here. At the beginning, these 3 protons were acting on this 3 electron, 1, 2, 3 electron. So this one, it was easy to remove. So when we remove, the total force of the proton is experienced by only 2 electrons. So they are even attracted with a greater force, right? So, and then we are removing the electron from the second orbit, which is very small orbit. And then it takes a lot of energy here. Now, third ionization energy, when you remove this one, now you have 3 protons, and 3 proton is acting only on 1 electron. So it takes even greater energy to remove third electron. Make sense? So that is 11,815. So you need 8,015 kilojoule. All right. So from the lithium, if you want to remove the outermost electron, you just give 514 kilojoule, and the electron is gone. If you want to remove another electron from the second orbit from here, you need to give 7,298 kilojoule, and then this electron is gone. And if you want to remove another electron from here, you need to give 11,815 kilojoule, and all electrons now are gone. Yeah. So as you remove more and more electrons, you need to give more and more energy from outside to remove that electron. Yeah. Listen, it's pretty easy, right? It's very easy. So now, there are a couple of things. So it is very hard to remove the electron from either half-filled cell if the orbit is orbit or orbital. If orbit or orbital is fully filled, meaning 8 electrons. So although there are 2n square rule I taught last time, but don't go up to that. 2n square is that too big. So if orbit or is fully filled, fully filled means 8 electron or 2 electron. So if in hydrogen and helium there is only 1 orbit. So fully filled means this has 2 electrons, this should be 2 electrons for hydrogen and helium. For other atoms, orbital is fully filled means they have the 8 electron. It takes too much energy to break that cell. Yeah. So the ionization energy is very high. Yeah. Good. So if the orbit or orbital is fully filled or half filled, they are very stable. And we need to give a lot of energy to remove the electron. Yeah. So this is one of the quantum mechanics outcome. So if the orbital is half filled, or the orbit is half filled, or orbit is half filled or fully filled, it is very, very hard to remove the electron. Yeah. So we will look this kind of thing in next slide. So let's look the slide number 12 first. Slide number 12, and then I will come to the slide number 11. Yeah. Let's look slide number 12. So that's anomalies in ionization energy. Anomalies means something that doesn't happen as we expected, right? Anomalies means it's out of expectation. So let's look at slide number 12. So lithium, look at the electronic configuration of lithium. So that is 1s, so number, this is third box, so 1s2, 2s1. So that's a lithium, right? Hydrogen, helium, lithium, right? So look, draw the electronic configuration. Look at the beryllium. So beryllium is 1s2, 2s2. So we already practiced it, and I think you already know it. Now boron. Boron is number 5. So this is 1s2, 2s2, 2p1. So carbon. Carbon is 1s2, 2s2, 2p2. Now carbon. After carbon, we have nitrogen. We have nitrogen. 1s2, 2s2, 2p3. Then we have fluorine, nitrogen, oxygen. Now we have oxygen. Oxygen we have 1s2, 2s2, 2p4, like this. And then we have fluorine, that is 1s2, 2s2, 2p4. Then we have neon, 1s2, 2s2, 2p6. So we have this electronic configuration, right? Now look, where is the half filled or fully filled or half filled? So basically, we are going to look the fully filled first. So don't look this one, that's a too large orbit. Now look it here. So this is a 2s2. If you want to remove the electron from beryllium, you have to remove the electron from the s2, right? 2s2. So the s orbital is fully filled. One orbital can have 2 electrons, and that orbital is already full, right? So it takes a lot of energy to remove this electron. Make sense? Why first ionization energy or the ionization energy of the beryllium is very high? Because the outermost orbit has 2s2 configuration, so it is already fully filled. One orbital can have maximum of 2 electrons, right? So it's fully filled, so it takes a lot of energy to take this electron. So if you see here, lithium, to remove this electron, you need to give 520 kilojoule. But to remove this one, you need to give 899. Now go to the boron, you just need 801. You see here? So because we are moving like this, lithium, beryllium, boron, carbon, like this. So I told you, if you go from left to right, the ionization energy increases, right? But here you see, lithium has 520, beryllium has 899, but boron has 801. So this is higher. So this is beryllium is 899. This is 801 only. So why we would expect if beryllium is 899, I would expect boron to be maybe 930, right? But this is too high. Why too high? Why beryllium is too high? Why it is not following the trend, right? Because beryllium has in outermost orbit, it has 2s2 configuration. The s orbital is full, and it is very hard to break the full orbital to remove the electron. Make sense? So like that. Now let's go to the other is fine. So let's go to here, nitrogen. Look here. So from where we need to remove the electron here? From 2p3, right? In nitrogen, we need to remove the electron from 2p3. So how many electrons can P can have? 6, right? Because P has 3 boxes like this. So Px, Py, this is Px, Py, Pz. So this can have 1 here, and another. It can have 6 electrons, but either 6 or half. So if there are 3 electrons, it is very hard to break this cell, the electron from there and remove it. Yeah, because it is half. Make sense? So why nitrogen has too high ionization energy than we expect? Because nitrogen has outermost electronic configuration 2p3, which is half filled, and it takes a lot of energy to remove the electron from the half filled orbital. Make sense? Good. So this has very high. So just look those. So this one is the anomaly. This one is the anomaly. Now let's go to maybe this is 5 here. Now this 4 is not half filled or full filled. This is 5. This is 5 is also not half filled, not full filled, right? Either it should be 3 or 6, right? If it is a p orbital. Now look here, P6. It takes a lot of energy to remove the electron from this neon. Why? Because p orbital has 6 electrons. The 66 is a fully filled orbital. So it takes a lot of energy to take out the electron from there. Make sense? So neon never react with anything. So you will never see any compound with neon. Why? Because the neon has the outermost, that p orbital is fully filled. So it takes a lot of energy to remove that. So nobody can remove that electron that easily. So neon never reacts. Yeah. So group 8 elements. So neon, argon, xenon. So if you look the last column in the periodic table, they never react. They are inert element. Why? Because they are fully filled orbital. So we cannot remove the electron. So if the electron cannot be removed, that means that they are not reactive. Yeah. So this is called the anomalies. Because so people just try to make the ions, they could not make the ion, and they say, oh, why we cannot make the ion? And they found that, oh, okay, either they are half filled or full filled. So if they are half filled and full filled in the outermost orbit, they cannot be removed easily. Yeah, good. So look the beryllium, look nitrogen, and look neon. So they are anomalies there. So they take too much energy to remove the electron. Now. So same thing. Further now we go and look the electron affinity. So we just finished the. I need to go back to that 11 slide number 11. I did not talk that one. So in slide number 11, so it is basically saying the first electron, second electron, third electron for the magnesium. So this is the ionization energy. So so slide number 11 is the same thing. So. They were talking about the magnesium there. So the magnesium, let's talk about the magnesium. So the magnesium. So magnesium has outermost, so in like this. So this is the magnesium. So this is a proton, neutron. So proton is 12. So there are 12 proton in magnesium. So in first orbit there are 2 electrons, and outer 2, 1, 2, 3, 4, 5, 6, 7, 8, and outer there are 2 electrons. So magnesium looks like this, right? So this is a slide number 11. I'm talking in slide number 11. So if you want to remove this first electron, you just give 738 kilojoule of energy, kilojoule per mole of energy. Why? Because it is too far from the nucleus, and it is easy to give the remove the electron if the electron is too far from the nucleus, right? Now, if you want to remove the second electron from here, so this you already remove this one, now it becomes the plus charge, right? Once you remove the electron, it becomes the plus charge, right? Now, if you want to remove the another electron, previously this proton was pulling these 2 electrons from the outermost orbit. Now this proton is fully exerting its force on only 1 electron. So pull becomes more. Make sense? In ions, pull becomes more. So previously there are 2 electrons, and then this proton force was divided between this and this electron. So by just giving the small amount of energy, you could remove this one. Now there are still 12 protons, and now previously it was working on 2 electrons. Now it is only working, this 12 proton is only working on 1 electron to pull toward this. So it takes more energy. Make sense? Good. So if you want to remove that electron, then that you give 1451 kilojoule. 51 kilojoule per mole. There are 6.023 10 to the power 23 atoms we are talking about, right? Now second is gone. Now let's talk about the third ionization energy. Now 2 are gone. Now this is a plus. This is also plus. There are already 2 plus. Now these 12 protons now are working on this inner orbit electron, which is the size is smaller, the radius is smaller. So this and also 1, 2, 3, 4, 5, 6, 7, 8. So this is also full cell, right? Full cell. So full cell, it is very hard to remove the electron from here. So if you want to remove the electron from here, so the third. So this was ionization energy 1. This is ionization energy 2. This is ionization energy 3. So To remove the third electron, you need to apply 7. How much is that? 1450. 7,732 kilojoule. Yeah? So why it is easy to remove the first electron? Because it's a neutral atom, and then the electrons are too far from the center, so it is easy to remove the first electron. Easy. Just give a small amount of energy. Now, once you remove the first electron, now you have only one electron in the outermost orbit, so the protons are working only to this electron. Previously, they were working in the 2 electron, now it's only working in the 1 electron, right? So they are pulling that electron with a great force. So second ionization energy is very high. Now the third ionization energy. Now you have already removed the 2 from there. Now, if you want to remove the third electron, you need to remove from the inner orbit here. So inner orbit is small orbit, and then it is also full orbit. So it takes a lot of energy to break the cell and remove that 1 electron. Make sense? So third ionization energy is too high. Yeah? Good. Now let's go to the electron affinity. So we are done with the electron affinity. So take extra care for the half filled and fully filled orbital. Yeah. So if you see the S2, it takes a large amount of energy to remove the electron from the S2. If you see the P3, it takes large amount of energy to remove the electron from P3. If you see P6, it takes a lot of energy to remove the electron from P6. If you see D5, that's a d orbital can have 10 electrons. So if you see D5, that's half filled. So it takes a lot of energy to remove the D5 electron. If you see D10, D10 is a full fill orbital, because D10 is a d orbital can have 10 electrons. So it takes a large amount of energy to remove the 1 electron from the D10 orbital. Makes sense? D10 configuration. So I'm telling you, what I'm telling you is that, so if you see something like this in outermost orbit, so let's say in outermost electronic configuration, write the electronic configuration, and last electronic configuration is something like S2, or last electronic configuration is like P3. So last electronic configuration is something like P6. Last electronic configuration is like D5 or D10. So if you see this kind of the configuration at the end of the electronic configuration, the ionization energy is too high. Make sense? Good. So something like this. Now, so I think when I was teaching the chromium and copper, I told you this concept, right? At the end of the chromium, we were writing something like the D5 or D5, 4s1, D5, something like this, 4s1, D5. So it takes a lot of energy to remove this D5 electron. In copper, I think we were writing like the 4s1, D10, 3D10. 3D10. So it takes a lot of energy to remove the electron from this D10 orbital. Make sense? Because they are either half filled or fully filled. Good. So this is very important. Now, if the box diagram is there, like this. So if this is P, like this. So it takes a lot of energy to remove this electron. But if something like this, it's very easy to remove this electron here. Make sense? So this is half filled. This is P3. This is P4. So it is very, very hard to remove one of those electrons, but it is pretty much easy to remove that kind of electron. Make sense? Good. Now, if you look in the D, let's say 1, 2, 3, 1, 2, 3, 4, 5. So let's say 1, 1, 1, 1, 1. So it's very hard to remove this. So this is D5 configuration. It's very hard to remove this electron. Too high ionization energy. If something like this here, D6, it's easy to remove one of the electron from here. Make sense? Now, if there was something like this, 10, 2, 4, 6, 8, 10, so it's fully filled. It's too much energy is needed to remove the electron from there. High ionization energy. Yeah? Did I make it clear? Good. All right. So now let's talk about the electron affinity. Electron affinity. So it's opposite of the electron negativity. Ionization energy. What we previously studied, the ionization energy is just the opposite of the ionization energy, right? So let's say you have a atom which is in the ground state. Let's say this is a chlorine atom. So it's in the ground state. It has not absorbed any energy previously, ground state means, yeah? And it is in the gaseous atom. So this is in the ground state, this is in the gaseous state. Now you are putting one electron. Previously I was removing one electron from here, right? Now I am putting one electron in its outermost orbit. Make sense? And when it takes the electron, it becomes chlorine minus. Previously, what we were doing? We were doing like this. We have potassium, and I was giving some energy, and then I was removing the electrons. Previously, in ionization potential, I was doing this, right? But this is ionization potential. Now, in this case, we have a gaseous atom. It is in the ground state, meaning that it has not absorbed any energy previously. Now, I want to put one electron from outside there, and how much energy is released, I want to measure that one. So that amount of energy is minus 349 kilojoule per mole. Meaning that, let's say you have a vessel here, and you have 6.023 10 to the power 23 atoms of chlorine here, and they are all in gaseous state, and they are in the ground state. They have not absorbed any energy previously, right? Now I want to put from outside 6.023 10 to the power 23 electron here. So there are the chlorine atom. These are 6.023 10 to the power 23 chlorine atom are here. Now I want to dump 6.023 10 to the power 23 electron in this container, right? And then all these 6.0, each of the chlorine take one electron, and I want to measure how hot this vessel is become. So that vessel becomes 349 kilojoule per mole hot. It's hot. It's exothermic reaction. Listen. Why minus there? Because the energy just come out and the vessel become hot. Yeah. Good. So it's an exothermic reaction. So the vessel was cold at the beginning. There was a chlorine. The vessel was cold, and I put this many electrons here and just shake it for a while, and I just touch it, and it becomes hot. It becomes hot, warm. Yeah. And if I measure this, how much heat was evolved? Was this much? 349 kilojoule heat was evolved. Minus sign says that it was evolved. Exothermic reaction when we studied in thermodynamics. Yeah. Make sense? Good. So previously I was putting the heat for the ionization energy, right? So that was endothermic. This is exothermic. Yeah. Good. So when we do the electron affinity, ionization energy, we put plus sign here because we are giving heat here to remove the electron. But in electron affinity, we need to put minus here because the heat is coming out from the reaction and the vessel is becoming hot. Yeah. Good. Make sense? Good. So now same thing. Now let's talk about the periodic trend. So what is the electron affinity? Electron affinity is an atom should be in gaseous state and is in the ground state, and we want to put one electron from outside to that atom, and that system gives a lot of energy out, yeah, exothermic, and the system becomes hot, and the amount of energy is called electron affinity. Yeah, good. So what happens to electron affinity? So let's go to the slide number 14. So basically, I have written a lot of words in the slide number 13, but it is saying the same thing in the 14 too. So let's go to slide number 14. So look the periodic table. So hydrogen is here, lithium is here, sodium is here, and the hydrogen. So let's say after lithium we have beryllium here, and boron here, then carbon, nitrogen, oxygen, fluorine, neon, like this. So if you put electron to hydrogen atom, so it gives out 73 kilojoule of energy out. There is a minus 73. Minus 73 means that 73 kilojoule energy is coming out as a heat. Yeah, minus 73. So lithium will give a 60 kilojoule out. And then sodium would give 53 kilojoule out. So minus, minus, minus. That minus meaning that energy is coming out. So I didn't write a minus here. Make sense? Good. So what is happening here? If you go from hydrogen to sodium like this, the electron affinity value is decreasing, right? Make sense? Electron affinity value is decreasing, meaning that hydrogen can easily accept incoming electron, but lithium doesn't want to be lithium doesn't want to accept the incoming electron. Sodium, even it doesn't want to accept incoming electron. If you go to the lower here, rubidium. So it's a rubidium. Rubidium is 47. So this means that this guy easily want to take the incoming electron. Make sense? This guy doesn't want. This guy still it's very hard to add electron here. It's very hard to add electron here. So if you see the electron affinity value here, if the number are small, they don't want to take the electron in them. Make sense? Why? Because they are too big. So this is very small. This is very small. This is very small. Hydrogen is very small, so the proton is here, and the one electron is here. If electron is coming from here, so this proton can easily influence this incoming electron and say, okay, come here, come here, come here. So it just attract this electron here and want to put it here. Make sense? So it is easy. The proton can easily pull the incoming electron. Yeah, and it gives out a lot of amount of energy out. Yeah. Good. Now let's look at the lithium. So lithium is like this. So 2 electrons are here, 3 protons are here, and then 1 electron is here in lithium because it's number 3. So 1 electron is coming from here to come to sit here, but this proton cannot influence that because it's too far. So from here to this distance is too far. So this electron doesn't come that easily to sit there because it's too far from the attraction of the proton. Make sense? So it's not willing to take that incoming electron compared to hydrogen. Hydrogen is very electron hungry kind of thing. Lithium is not that electron hungry species. Now let's go to the rubidium here. Let's go to the sodium. Sodium is a number 11. So proton, there are 11. So first are 2 electrons. Second, 1, 2, 3, 4, 5, 6, 7, 8. And then 1 is here. So now incoming electron should be heading to third orbit. And this 11 proton cannot tell this incoming electron easily and sit here because the third orbit is too far. So this 11 proton cannot attract this incoming electron that easily. So it's not willing to take that electron very well. Make sense? I don't know if I make it clear. So if the electron is being added to the far orbit, those protons cannot attract easily that incoming electron, and they only if anyhow it takes that electron, it gives a small amount of energy. Yeah. So basically, electron affinity is saying that what is electron? Electron is electron. Affinity. What is affinity? Affinity is attraction towards somebody, right? Affinity is it's attraction with somebody. So meaning that the hydrogen has a large electron affinity, meaning that it wants another electron come here and sit here. Lithium has a small electron affinity. Lithium doesn't want another electron coming and sitting with this lithium. So sodium, small electron affinity. Sodium doesn't want another electron coming and sitting with this one. But if anyway another electron come and sit there, it releases a small amount of energy. So small electron affinity means these atoms don't want to take the electron easy. Make sense? Good? All right. So now let's talk about the. So as you go down in the group, size becomes bigger, and the atom cannot attract the incoming electron easily. So now let's go from the left to right. So lithium is here, the beryllium is here, and boron is here. So here in lithium, you have a 60 kilojoule. If you add 1 electron, it gives out 60 kilojoule energy. In beryllium, 0. Boron, 27. Now let's look at the nitrogen, 0. And then let's look at the neon, it's also 0. Look these elements. So there are anomalies. So in lithium, you can add electron. There's large electron affinity. But beryllium, you cannot add electron. It's a 0. Why? Because if you look at the electronic configuration of this one, 1s2, 2s2. So the outermost orbital is already full, right? If you want to, so if something is full or something is half, and you are trying to add the electron there, it doesn't want to accept the electron because it's already satisfied. With full and with half, it is already satisfied. Make sense? So It's a boron. It's good. So boron, the size is smaller. As you go this way, size. So this boron has a small. How much is it? Small electron affinity. And you go to the nitrogen here. Nitrogen is 0. Why nitrogen has small electron affinity? Because it's like this. So 1s2, 2s2, 2p, 3. If you look the outermost orbital here, 2p3. So this is half filled. So nitrogen doesn't want to accept the incoming electron easily. It's already 2p3. If you get the 2p1 electron and it becomes 2p4, it becomes unstable. So nobody wants to be unstable. They want to be stable, right? So like that. So this has very small electron affinity. Pretty much nitrogen cannot accept incoming electron. How about the neon? Look at neon here. 1s2, 2s2, 2p6. So like this. So neon has in outermost there are the 6 electrons in the p orbital. So this is already stable. So it doesn't want to accept the incoming electron. Make sense? So if it's a half filled or full filled, you need to be extra care for that. You need to take extra care why something is not working everything. Yeah? Good. Now, let's look the oxygen here, between the oxygen and fluorine. So let's look the oxygen here. Nitrogen, here is oxygen, here is a fluorine. If you look the oxygen here, nitrogen is 0 because of the half field. But if you look the oxygen here, it's a 141. And if you look the fluorine, 328, like this. So why oxygen is a large value? Because in outermost orbit, oxygen has 6 electrons, right? So they are trying to have other 2 electrons so that they become full. Make sense? So they have pretty good electron affinity. How about the fluorine? So in outermost orbit, this is in the 7th group. So outermost orbit of fluorine has 7 electrons. So it is a kind of the electron hungry. So it is trying to find 1 electron from outside so that it becomes stable. Yeah. Make sense? Good. So, so this guy doesn't want to have electron. This guy wants electron. This guy wants to have electron, but not as effective as this one. Fluorine is very electron hungry species. So fluorine wants to have the electron because it has outermost orbit. There are 7 electrons. So if it takes 1 electron, it becomes 8, right? So like that. So you can read there, and then here are a couple of things I just want to read here. Now, so if you look the fluorine here and chlorine here, fluorine is 328. So this is 328 and chlorine is 349. So why fluorine doesn't want to take electron that easily, but chlorine want to take electron very well, right? That means that because it has an electron affinity 149, so it is very electron hungry. But this is not that much electron hungry. Why? Because this is like this. So fluorine is, if you draw the fluorine, so fluorine is a 1, 2, 3, 4, 5, 6, 7, 8, 9, right? So ninth box. So if you look here, 2 here, and then 7 here. 1, 2, 3, 4, 5, 6, 7. So total 9 here, like this. If you look at chlorine, chlorine is a 9, 10, 11, 12, 13, 14, 15, 16, 17 box. So if you look at the chlorine, this is a proton 17. So 1, 2 in the first, and then 1, 2, 3, 4, 5, 6, 7, 8 in the second, and then in the outermost 1, 2, 4, 5, 6, 7. So you see here, in the fluorine, this second cell is smaller. So there is an electron crowded. It's already crowded with electron, right? So if another electron wants to come there and sit there, the electron already there want to push this out. So there are the 7 electrons in this one. The cell is very small. House is very small here. So this electron want to come and sit here. But what this 1, 2, 3, 4, 5, 6, 7 electrons say? Oh, we are already crowded here, so we don't want you to come and sit here. So this atom doesn't want to accept that electron easily. Make sense? Because the electron already there want to push that incoming electron out. Make sense? But if you look here, this house, the third house is too big. 1, 2, 3, 4, 5, 6, 7. The third house is very, very big, and if someone comes here, this atom say, oh, okay, you can come and sit here because we have too much space. So it can easily accept the incoming electron. Make sense? So this has large electron affinity. Chlorine has large electron affinity. Fluorine has small electron affinity. Make sense? Good. So I wrote those kind of small notes there. You can. I think we are done. So we will continue in the next class. Yeah. So I thought I would finish today, but I couldn't finish. That's okay. Alrighty. Thank you very much, everyone. So just read those small notes there, and if you have any question, you can let me know.